Howdy, we are Team Stabilicore, and welcome to our presentation for the Engineering Project Showcase. I'll go ahead and start by introducing ourselves. So my name is Macy McClooney, and alongside me is Nathaniel Blevins, Truth Shuraith, and Elias Sanchez. Our sponsor and advisor is Dr. Kim, and her previous research experience includes human behaviors and neurological disorders, which ties directly into our project. So to give a overview of what our balance board will entail. So currently, a problem that the world faces is that people come in to physical therapists with damaged nerve endings, and this causes some unbalancing problems. And so they need physical therapy, and the existing products are rather expensive and bulky, as seen in the image on the left-hand side. And there are also non-mechanical tools that can be used to combat this problem. But however, the problem with those is that they require personal assistance from the physical therapist. And so what we plan to create is a magnetic controlled balance board that will be a more affordable and effective way to combat these side effects while providing a personalized physical therapy treatment plan.
So in order to create a product that is competitive in the market, we've defined a list of functional requirements. The first being that our product is more portable than any other product currently on the market. We are designing a product that has a 2x2 footprint that can sustain up to 350 pounds for every type of user. Is battery powered to reduce the need to be plugged into a wall without sacrificing the stability that bulky products offer. So we will have a handle that will help users who have imbalance issues, which our product is designed for, and a user interface that is wireless so that we can control it from a laptop.
So this is a representation of the conceptual block diagram. As seen in the image on the left, this is what we expect our balance board to look like. So it's going to be comprised of three main layers: the platform layer, which houses the sensor mat, which is used for positioning of the person using it; the middle layer, which is the lightweight non-magnetic outer shell, which is in the shape of a hemisphere, and inside the hemisphere will be magnetic material. And in the base unit layer will be a grid of electromagnets and ball bearings. The ball bearings are there to make sure that the hemisphere shifts smoothly, so in turn it tilts the board accurately. And the electromagnets are going to be used to move the magnetic material around. So for example, when a user sends the command that he wants to tilt the board to a top left position, he will activate the top left electromagnet using the program, and that electromagnet will activate, and this will cause the movable magnetic material inside to shift to the location of that magnet. And as it does this, it will cause the hemisphere to tilt accordingly and will cause the balance board to tilt as well.
Looking at the devices that we'll include in our design, we'll have two little-color batteries, one being the 3S5P that is 12 volts, 10 amp hours, and the 7S4P that is 24 volts, 10 amp hours. Our two voltage regulators are going to be a 12 or 24 volt to 5 volt regulator and a 12 or 20 to 3.3 volt regulator for our sensors and microcontroller. The PCB will handle that sort of power distribution. The magnets we've chosen are UXL magnets, which are 12 volts DC and have about a 1400 Newton lifting force. They'll be arranged in a 3x3 grid.
So in order to handle the 3x3 grid of electromagnets, we are planning on having a ESP32 microcontroller that has 16 PWM digital pins to control the 9 electromagnets that we are planning on using. In addition to this, it has the serial connections needed to connect to all of the peripherals that we're going to be using to sense the angle and the just overall data that the board is processing. The ESP32 also has built-in Bluetooth that will be able to connect to the desktop application that we are designing to communicate to the board.
The main sensor that we've chosen is a 9 degrees of freedom sensor. It's going to be utilizing a 3-axis accelerometer, gyroscope, and magnetometer. Additionally, we'll have 2 3-axis accelerometers and a Kitronic sensor mat, which will be used to actually understand where people are and balanced on our board.
The final sensor that we're going to be including into our design is the Snowboard 2 Plus, which will work with the matrix that the Kitronics sensor mat provides in order to translate the resistive sensors into sensor or pressure sensor data of the user standing on the board. So it will be able to create a user center of pressure that can be sensed in real time and sent to the desktop application through our microcontroller. So moving on to the desktop application portion of the software, we will be having both hard-coded therapy programs that can kind of be used to get a general idea of the patient's progress in their physical therapy program, and also custom-made programs that the physician can code themselves in order to have a more personalized physical therapy experience. And so because of this, we will be also creating a user guide that will instruct the user on creating these custom programs, in addition to the program having a real-time visualization of the sensor mat data in real time.
So as mentioned earlier, the entire system is going to be powered by two batteries. So the first battery is going to be a 12-volt system that powers the voltage regulators, which sends power to all the electronic equipments, such as the accelerometers, the magnetometer, gyroscope, accelerometer combo, the ESP32, and also the Snowboard 2 Plus. The PWM signals from the microcontroller itself will be sent to relays, which when a particular relay is activated, each of those relays is connected directly to the electromagnet. So when a relay is activated, the electromagnet will turn on and it will move the magnetic material to its appropriate location. So moving on to the electromagnet grid, this is just a representation of how it will be located on the top portion of the base unit layer. Each electromagnet will receive about 20 volts of power, and it's going to be activated from the PWM signal that's sent to the relay that's connected to each electromagnet. And the sensor mat layer, on the sensor mat layer is where our accelerometers are going to be located, one on each end, so we can gauge the position of the board and gauge how it's tilting in real time. So this information is directly sent to the microcontroller, and the microcontroller controls the tilt and everything of the board. The sensor mat itself, it has its power delivered from the Snowboard 2 Plus, and it also transmits data to the Snowboard 2 Plus.
Finally, we want to go back over what we've talked about by saying that we want to create a magnetic controlled balance board, a user interface that's usable and understandable, as well as a user's guide. We want to be able to have visualized data to help physicians create a therapy plan, and we'd like to make our board a competitive price. We hope that it can help in the applications of physical therapy sessions, but also at home. We hope that it can alleviate costs for people that do go through physical therapy and hopefully be used in further medical research. Thank you for your time.